Have you ever wondered why every airplane window is round? Not oval, not square, not even a rectangle with soft edges round. At first glance, it seems like a minor design detail. Something a designer picked because it looks friendly, or because it's easier to see out of. But, in aviation, nothing about the shape of a structural opening is left to taste. Every curve, every radius, every millimeter of a window frame is the result of a calculation, and the round shape of an airplane window is one of the most quietly important decisions in the entire aircraft. When people try to explain it, the answers are usually simple. The first is visibility. A round window seems to offer a wide, unobstructed view. The second is aesthetics. Rounded shapes look modern, smooth, and pleasant against the curve of the fuselage. Both explanations sound reasonable, and to some extent, they're true, but they don't explain the real reason. If this were only about looks or visibility, windows could be square with slightly rounded corners, or tall and narrow, or almost any shape that lets light in. Airlines have experimented with plenty of window shapes over the decades. But engineers don't leave this to preference, because the real question isn't what the window looks like, it's what happens to the metal around it every single time the aircraft climbs and descends. We're not just talking about a hole cut into a wall, we're talking about a hole cut into a pressure vessel that inflates and deflates thousands of times over its lifetime. And at that point, the problem changes. It's no longer about how the window looks, it's about how the surrounding structure survives decades of repeated stress. To understand that, we need to look at one of the most critical concepts in aircraft structures: stress concentration. When an aircraft climbs to cruising altitude, the air outside becomes thin and cold, but the cabin stays pressurized to a comfortable level. That means the fuselage is essentially a sealed tube being pumped up like a balloon on every single flight, then let down again on every landing. Multiply that by tens of thousands of flights over an aircraft's service life, and the fuselage skin is absorbing an enormous number of stress cycles. Now imagine cutting a hole in that skin. If the hole has sharp corners, the stress doesn't spread evenly around it. It concentrates at the corners, sometimes at levels several times higher than the surrounding material. Over thousands of pressurization cycles, that concentrated stress can produce tiny cracks, and those tiny cracks grow. That's the core problem. So engineers shape every opening in a pressurized fuselage, windows, doors, even inspection panels to remove sharp corners entirely, and that's why the shape is round. A round or rounded oval opening spreads stress evenly around its entire edge, with no single point taking a disproportionate load. As the fuselage repeatedly inflates and deflates, the round window barely notices. But even that doesn't explain everything. If this were purely theoretical, engineers might have discovered it gradually through testing and simulation over the decades. In reality, this lesson was learned the hardest way possible. In the early 1950s, the de Havilland Comet became the world's first commercial jet airliner, and it had squarish windows with rounded corners that still weren't round enough. Within 2 years, several Comets broke apart in flight. Investigators from the Royal Aircraft Establishment eventually traced the failures back to metal fatigue that started at the corners of the window frames, exactly where stress concentrated most. That investigation reshaped how every pressurized aircraft has been designed ever since. It's the reason round windows aren't a stylistic choice. They're a direct engineering response to one of the deadliest lessons in aviation history. When you look at a modern airplane window from the outside, it looks small and simple. But in reality, it's a carefully engineered assembly. Most aircraft windows aren't a single pane, they're actually 3 layers. The outer pane bears the pressure difference between the cabin and the thin outside air. The middle pane is a backup in case the outer pane fails. And the inner pane, the one passengers touch, is mostly there to protect it lets cabin air pressure act on the middle pane instead of the outer one, so, under normal conditions, the outer pane carries almost the entire structural load, while the middle pane stays as a reserve. This is why a small scratch or a bit of fogging you sometimes see on a plane window isn't a defect, it's condensation forming exactly where engineers designed it to form. But there's another factor, and this is where the design becomes truly elegant. The round window isn't solving its own problem in isolation, it's part of a much larger structural philosophy that runs through the entire fuselage. Take a modern aircraft like the Boeing 787 or the Airbus A350. Their fuselages are built largely from composite materials instead of aluminum, and composites behave differently under repeated stress than metal does. Engineers actually increased window size on the 787 compared to older aircraft, because the WWW composite fuselage tolerates stress concentration differently, and better cabin pressurization systems allow a lower effective cabin altitude, meaning less pressure differential stress overall. In other words, as the surrounding technology changed, engineers didn't abandon the round window principle, they recalculated exactly how far they could push it. To see how far this philosophy extends, look at the doors. Every hole cut into a pressurized aircraft fuselage follows the same logic that shaped the window, which is why aircraft doors are never simply rectangular either. Their corners are always rounded to the same degree the structure requires, and their edges follow curved load paths engineered to avoid stress concentration. But doors carry an even bigger structural burden than windows, because they're not just openings, they're openings that have to reseal thousands of times and hold back the full force of cabin pressure at altitude. And this is where a piece of aircraft design becomes almost impossible to believe the first time. You hear it. Most airliner doors are what's called plug doors. At altitude, the pressure inside the cabin is higher than the pressure outside, and that pressure difference literally pushes the door into its frame from the inside, the same way a plug is pushed into a drain. The door is shaped slightly larger than the opening on the inside, so no matter how hard someone pushed on it mid-flight, the cabin pressure itself is holding it shut with a force far beyond human strength. It's not the lock that keeps a plane door closed at 35,000 feet, it's physics. To open it, the door first has to move slightly inward before it can rotate outward, and at cruising altitude, the pressure differential makes that inward motion essentially impossible. That's why flight attendants can open the same door effortlessly once the aircraft lands, and the cabin pressure equalizes with the outside air. The design that keeps a window from cracking, and the design that keeps a door from ever opening in flight, come from the exact same engineering instinct. Remove sharp transitions, respect the pressure differential, and let the shape of the structure do the work that force alone never could. And this is exactly what makes aircraft engineering so fascinating. The most important decisions are often the ones passengers never think twice about. A rounded pane of glass, a curved door frame, a bleed hole the size of a pinhole, all of it works quietly. In the background, absorbing tens of thousands of pressure cycles over a lifetime of flights, it's easy to look at a window and see nothing more than a place to watch the clouds go by. But behind that curve is one of the most expensive lessons aviation ever learned, and one of the clearest examples of how, in engineering, the shape of something isn't chosen for how it looks. It's chosen for how it survives. What other everyday details on a plane do you think are secretly engineered like this? Let us know in the comments.